Hey everyone, welcome back. Today we're diving into COMSOL Multiphysics to model a classic parallel plate capacitor. What you find in this tutorial: how to simulate ideal parallel plate capacitor in COMSOL Multiphysics, how to define the model in parametric form, how to set boundary conditions, how to explore results, how to add equipotential lines to graphs, how to add cut line to the model and plot a value on that line, and how to calculate the capacitance of the structure. Be with me. Okay, I'm at the starting screen of the COMSOL Multiphysics. I go and click on Model Wizard. Let's see our capacitor structure. Here is the capacitor structure. We have two conductive plates and a dielectric material with relative permittivity of epsilon r between these two plates, which you can see here. The separating distance between plates is d. I explain later why it is double d. The length of the plate is LL and the width of the plate is WW. The dielectric in this model is ideal, which means it has no conductivity. It is not a real case, but it can be assumed that a dielectric has no conductivity. Okay, for modeling this capacitor, I use the 2D space dimension. I'm looking to this model from this side. I see LL and DD, and then I define WW as depth of my model. Okay, come back to COMSOL, selecting 2D. For the physics, we only need to add the electrostatics. The electrostatics is the physics that solves Gauss's law and also the Laplace equation. It does not consider conductivity, it only considers permittivity. It is sufficient for our model. Click on Add. Then we are going to study. In this video, we explore only stationary study. Since the dielectric is ideal, there is no difference between various frequencies. Therefore, the results of the stationary study is the same as the frequency domain, but I will explain time domain and frequency domain in my next video. Okay, I have selected the stationary and finally I click on Done. Okay, the first step would be the geometry. Let's get back to the sketch of our capacitor. I have considered these parameters for my model: the separation distance 1 cm, the width and length of the parallel plate 10 cm, and the relative permittivity epsilon r equals 4. Okay, click on geometry. As our capacitor is in centimeter, it's better to set the length unit to centimeter. It is much easier, but you can also work with meter or any other option. Okay, the only thing that I need for this geometry is a rectangle. You can just click here on the geometry tab. You can find rectangle here, or right click on the geometry. I click on rectangle. Here you can see. Please set the type on solid because I want the rectangle to be solid. I want that rectangle having inner part. I want to define a domain, not a boundary. Okay, here is the width. It should be set to 10 cm. And here is the height. 1 cm is okay. And I set in a way that the center of the rectangle be the center of my coordinate. By clicking on Build, you can see the cross section of our capacitor, and if you just click here and set Build All, you can find our capacitor. I want to set the bottom line as the bottom plate, the upper line as the upper plate, and the left and right lines would be our boundaries. That should be an infinite boundary. Till now we have defined L and also D, but we haven't defined W. Let's get back. For this you should just click on the physics. because we are performing our simulation in 2D, here you can find another option, out of plane thickness. It is exactly the amount of WW, the amount of depth or thickness that comes out of plane. I set it to 0.1, in other words 10 centimeter, and I'm good to go. Okay, now I need to set a material for my dielectric. I just right click on add material from library. Here I search for quartz. It is a dielectric that has relative permittivity near 4. Here you can see quartz. There are different types of it, but the quartz in the AC/DC would work. Just add to component 1. I do not need this window, so I close it. Notice that automatically COMSOL assigns quartz to the only domain that I have. I have only one domain number 1, and it is now set to be quartz. If I click on this, you can see that this part is purple. If I remove this, for removing this domain from being quartz, just click on this and then click on minus. You can see remove from selection. And in this case, you see that the domain remains gray. But if the domain is in my selection, for this, just go on your domain and click on it. It comes here and you can see that it is quite purple. I should not forget to save my model. I'll do it like this. Okay, before moving on to boundary conditions, I want to explain something else. What if I want to change the dimension of my capacitor and also the permittivity of the dielectric later? What if I want to do a parametric sweep to see what are the effect of different parameters on my output? For this, I need to define the dimensions, the length, the width, and so on as parameters so I can change them later very easy. For this, beneath the global definition, you can find something that is set parameters. Click on this and here you can define parameters. Okay. For example, the first parameter, I set the name as DD. The expression would be 1 centimeter. The description can be distance between plates. Now I say why I set my parameters as 2 letters. For some letters, it is possible that this letter would be a predefined variable in COMSOL. For example, V is reserved for voltage, and so on. And to reduce the interference between my parameters and the reserved variable, I also use complex name for parameters, or I just repeat the name. Okay, the next one would be LL, that I set it to 10 centimeter. That is the length of plates. Then I set WW to 1.10. Why? Because in electrostatics, I cannot set it to centimeter. It is in meter. Therefore, it is the depth of plates. And also I define another parameter as EPS. I set it to 4, and this is the relative permittivity of my material. How do I use these parameters in my model? Quite simple. I come here. Instead of typing 10 in front of width, I just type LL. Here height, I type it DD. Nothing changed because it has the same dimension. Here I set it to WW. Here WW is depth. And to set my permittivity, I click on quartz. If I scroll down, here you can find the relative permittivity. Now it is 4.2. I set it to EPS. Please notice that there are several properties of quartz here, but only one of them has check mark, which is relative permittivity. It is the only property that is needed for this specific simulation which uses electrostatics. If you use another module that, for example, needs relative permeability, you can also see here another check mark. And if you do not define and set that parameter, you can find a red cross near it. Okay, now I have set all my parameters. How can I see that it works? Pretty simple. I come here and set the length of the plate to 5, press enter, and you can notice a little star near this rectangle. It says that by changing that parameter, the rectangle should be changed. I just come here and set build all objects. You can see that the dimension of my rectangle has been changed. Come back to parameters, set it for now to 10, enter, build all, and I am back to the previous state. Okay, now it is time to set my boundary and domain conditions. Here you can find a domain condition. The one that are solid, the symbols that are solid corresponds to a domain. The one that has this specific symbol correspond to boundaries. Here is charge conservation. If you just see the equation, it is the Laplace equation. It only uses the permittivity and also the charge density to find the voltage. It is okay, I want to solve the same thing here. Zero charge is now set to all boundaries. What means zero charge? Here you can see the equation n dot d equal 0. It says that on the boundaries that have this specific condition, the perpendicular component of electric field should be 0. You can only have tangential component of electric field. Let's go back to my sketch of the capacitor. As you can imagine, the type of electric field in an ideal capacitor is like this. And also everywhere we would have electric field lines such as this. As you can see, the electric field on the boundaries is tangential. There is no perpendicular component. Therefore, it is a proper boundary condition for the left or right line. But it is not true for the bottom and top plate. Right click on electrostatic. I want to set the bottom plate at ground potential. I click on ground and you just go on the desired boundary. It becomes red and then just left click. You can see that it has been added to my selection. Right click on electrostatics. I want to set an electric potential for the upper plate. Add it to my model. It says that the selection is empty. I come here, select the upper line and click on it. It has been set and I just enter 1 volt for the plate. Therefore, I have a capacitor that has 1 volt electric potential between its plates. Here is a good place to notice some tiny points. If you want to move your sketch here, the geometry, you have to right click and hold your right click and then you can move your geometry. If you want to zoom your geometry, you just press Ctrl and hold it and then work with the scroll button of the mouse. I have set all boundary conditions. Here also have an initial value. In complex simulations, it is important what value you give to initial condition. Here it is set 0 volt. It means that all the area have 0 volt at the start of our simulation. You can just leave it be, because for this simple simulation that does not matter. The next step would be meshing. For now you can just use the physics controlled mesh. If you kill it, you can see another option, user controlled mesh. This controlled mesh is okay for the electrostatics. And here you can set the element size of your mesh. If you go here, for example, cursor, and let's click on build all, you can see large meshes in your geometry. If you come here, for example, extra fine, you can see much smaller meshes that increase the accuracy of our simulation. Here I set it on extra fine, build all, and everything is ready. Just right click on study and click compute, and the software will calculate the voltage and electric field. Let's explore our results. Okay, first you should notice that these purple icons denote a 2D sketch. This sketch is a 2D plot of electric potential, and here is a 2D plot of electric field norm. If you just open the electric potential, you can see two different types of plotting: streamline and surface. The streamline are these lines that you can see here. It shows the electric field lines. For now, I just disable this because I don't need this. And surface is this coloring that you can see on the surface of your geometry. If you click on this, you can see that the expression here is V, which stands for electric potential. You can see also here above your result, electric potential on volt, and here you can see that the red color denotes 1 volt and the blue color denotes 0 volt. I always prefer rainbow classic coloring. If you want to change the coloring, you can see here an option, coloring in style. Click on it and you can find rainbow classic and any other things. Okay, you can see the electric potential here. It is the same as we expected. This is a very important point. You set some boundary conditions, set some physics for your model, and the software will calculate the output. You as an engineer should have the knowledge to analyze your output, to find out if your output is correct or wrong. This step is called validation. If you cannot validate your simulation, it has no value. A validated simulation can work. Okay, here I know that I have set here 0 volt and set 1 volt. Check number 1. Okay, it is correct. We should move from 0 volt to 1. If I want the electric potential on a specific point, you can just move your mouse to that specific point, for example here, and double click on that. You can see here the x value, x coordinate, y coordinate, and the value. This point has 0.6 volt. Okay, now I want to disable the surface here and enable these streamlines. If we click on streamlines, you can see that the x component and y component has been set to es.x, ex, and es.ey. If you want to see what is these things, you can just click here on reflex expression. You can just type it here, es.ex, and it is the electric field and the x component of electric field. Also, ey means the y component of electric field. You can also find different things here. I explain later how to add equipotential lines. Also, I explain how to use this option. These are the electric field lines. I have expected them to be perpendicular to the plates everywhere, and I can see this. Check number 2. My model works correctly. The color expression is here. If I set this or disable this color expression, you can see some black lines, but this color expression says that the coloring has been set on electric potential. It means that blue color denotes a lower electric potential, the red color denotes higher electric potential. Okay, now I want to add equipotential lines to my plot. I disable this. Right click on electric potential. You can see different options that you can use. If I use contour is a proper selection for plotting equipotential lines. I click on this. It is set to electric potential as a default. If you want to change it, just right click on here, reflex expression. You can see here all of the variables and parameters of your model. Here beneath electrostatics, you can find the energy and power, electric, and in the electric, there you go, you can see electric potential, V, which is in volt. For example, es.norm D means electric displacement field norm, and so on. You can find any parameter or variable that you need. Okay, V works good. I then click on plot, and these are the equipotential lines. As you see, all equipotential lines are parallel to my plates, and in an ideal parallel plate capacitor, this is the situation. There are also another way to, let's disable this, to show the electric field lines, and here is the arrow surface. It adds some arrows in all the surface of your domain. If I click on this, you can see that the default is the X and Y component of electric field. If I set plot, there you can see the arrows show the electric field, and it is true because the electric field should be from the higher voltage 1 volt to the lower voltage 0 volt. You can also set the amount of points. You can just play a little bit with these numbers. For example, I set this to 5 and also set this to 5 and plot. You can see that one number set how many lines you need on the Y direction and the X grid, and one set on Y grid. For example, I want 15 on the X grid and 5 on the Y grid. There you go, you can see this. There are also other options, but I do not want to explore all of them in this video. If I click on the next plot, I can find the electric field norm. I just disable the streamlines. On the surface, I need to see the electric field norm, which is the magnitude of electric field, and it says that the electric field everywhere is equal, which denotes a uniform electric field, and everywhere it is 100. If I want to change the unit of my display, just click on this. You can find different units here. I want to show my numbers in volt per centimeter. You cannot find a volt per centimeter here, but that's not a problem. Just click here and add a C. This is volt per centimeter. COMSOL recognize that. Set enter and plot. There you go. It is on volt per centimeter and it says 1. Is that okay? I would say yes, because for a uniform field, the amount of electric field equals V divided by D. I have 1 volt potential difference. D is 1 centimeter, so the electric field everywhere should be 1 volt per centimeter, and this is the case here. Now I want to calculate the amount of capacitance of this specific structure. For that, I should go to derived values. Derived values is for values that I want to get from the model. I right click on derived values. Here you can find a global evaluation. Global evaluation gets you the values that do not depend on 1 point, 1 line, and so on. I want to calculate the capacitance. The capacitance is not for 1 point or 1 domain. It's for all of my structure. Okay, I click on global evaluation. The expression is now empty. I just right click on replace expression. Here below electrostatics, you can find 2 options. In the energy and power, you can find the total electric energy. I just double click on this. It says that unit is joule, and I then click on evaluate. You can see a new table. It says that the total electric energy in this capacitor, which has 1 volt of potential difference, is this value. How can I calculate capacitance from this value? Okay, look at this expression. As you know, the amount of energy stored in a capacitor equals half C times V squared. C is the capacitance, V is the potential difference between plates, and here I have set the potential difference to 1. Therefore I should replace here 1, and therefore I can deduce that C equals 2 times the energy. The energy is this value. I just double it and I reach 3.54 times 10 to the power minus 11 farad, and equals 35 picofarad. Is it true? Is it correct? I can evaluate the capacitance of a parallel plate capacitor using this formula. I have a separate video on capacitors and specifically parallel plate capacitor. You can just watch it above to find out how this formula is derived. Okay, in this formula, I just replace everything that I have. A is the surface area of my plates, which are 10 centimeter multiplied by 10 centimeter. I just put everything in SI units, which is here meter. D is the separation distance, which is 1 centimeter. Epsilon R is the relative permittivity, which is here 4, and epsilon 0 is the permittivity of vacuum, which equals 8.85 times 10 to the power minus 12. If I substitute all of them, I reach 35 picofarad. There you go, my model works correctly. Here I get the energy of my capacitor first and then calculate the capacitance from that energy. Is there a method to calculate or derive the capacitance value directly? Yes, it is. How can I do that? I come back to electrostatics, and here I change the boundary condition of electric potential. I disable this and add another boundary condition, which is very useful. I just explained about it in my next video, how to connect a capacitor to an external circuit using this boundary condition. It's a terminal. I add the upper plate to the terminal condition, and here have different options. I set it on voltage and set 1 volt. It is quite similar to the previous boundary condition in this state. It assigns 1 volt to the upper plate. Okay, I have said that. I just recalculate the model, set compute. Okay, here you can find the electric field norm. As you can see, we are at the same state, 1 volt per centimeter. Now I come to global evaluations and click on replace expression. Here you can go into electrostatics. You can see an extra option here. It says terminals. If you click on terminals, you can see 3 variables: terminal voltage, terminal charge, and there you go, Maxwell capacitance in farads. If you just click on Maxwell capacitance in farad and just click on evaluate, there you go. This is my previous direct value. It is the new one, Maxwell capacitance farad. It says 3.54 times 10 to the power minus 11. It is the same thing that I have calculated here. Therefore, my model works correctly. Now I want to explain something else. What if I wanted to, for example, plot the electric potential along a specific line in my model, in my 2D model? For this, I just need to come here in dataset, right click on it. You can find something called cut line. It defines a line in your geometry, and then you can plot different values, different parameters over that line. Click on cut line. It needs the coordinates of the first point and the second point of the line. I want to set my lines here in the middle of my geometry. Therefore, point 1 would be here. The x is 0 and the y would be minus 0.5. Point 2 would be here and the x would be 0. The y would be plus 0.5. If you want to see if your cut line is correct, just click on plot. There you go, you can see your cut line. Now I want to plot a specific value on this line. For this, I click on results and add 1D plot group. Right click on 1D plot group. You can find different type of graphs that we can use. For this, we just go on line graph because we want to plot a value on a line. Okay, click on line graph. Okay. Here, if you select 1D plot group, you can see here a data set. Here you should define from what data set you should get your data. If you click on this, you can see a new option. It says cut line 2D. It is the same line that I defined here. If I set this, it plots something on that specific line. If I come here, I can define my expression the expression is set on electric potential, therefore it plots it. You can see here the electric potential on that line. Here on the y-axis, you can see the electric potential in volt. Here it says arc length. What is the meaning of arc length? If I plot the cut line, here is arc length of 0 centimeter, and here is the arc length of 1 centimeter from point 1 to point 2. If I want to plot the voltage versus the y-coordinate, which makes more sense, I just come here. You can see here the y-axis data. Here you can see x-axis data. It says arc length. Just click on it and says expression. For the expression, click on replace. Under the geometry and coordinate, you can find y-coordinate. If I replace this and unit is centimeter and plot this, there you go. Here from minus 0.5 centimeter to 0.5 centimeter, the electric potential has been plotted. Here is 0 and here is 1, the thing that I needed. If I want to plot the electric potential here, I just come here and under the electrostatics and electric, just select the electric field norm and set it to volt per centimeter. Plot. Oh, you can see something which should be a constant line because the electric field should be same everywhere. You can see some changes, but this is natural. Just look at the y-axis. It says 1, and here from here to here nothing has changed. If I come here and select the 1D plot group, I can manually set the y minimum and y maximum. I just set this. I set the y minimum to 1 point, for example 95, and y maximum to 1.05, plot it. And now you can see a constant line everywhere. But why it is not here constant? Because fellows, we are using a numerical method. A numerical method is different from the analytical solution most of the times. There is a specific amount of error between the output of a numerical simulation and the real situation or analytical solution. The point is, the amount of that error should be very small. Yes, there is very tiny, trivial differences between the electric field in different meshes, but the amount of that difference is very, very small. If I set it to this value and is to 1.001, you can see again a constant line, which says that the amount of those differences in the electric field is very, very, very small, and it is acceptable. Don't panic if you see something like this in your results. Okay, I think that's enough for this video. In the next video, I want to connect my capacitor to an external electrical circuit, and I want to perform frequency domain study and also the time domain study and measure the current profile of my capacitor. Be with me in my next video. If this video was helpful for you, just like it and recommend it to other people. Please subscribe to the channel and hit the notification bell so you don't miss my next videos. Till next time.